Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all to the class of real analysis. Our discussion is continue on the properties of supremum and infimum of a set. In today's lecture, we will discuss an important property related to infimum of a set. So to follow today's lecture, I hope you have a clear concept about infimum of a set. The property says that if S is any non-empty subset of R that is bounded below, and let A be any positive real number, we define a new set AS, which is actually the product of the real number A and the elements of set S. Then for this set we have to show infimum of AS is equal to A time infimum of S. This property is similar to property number 4. In property number 4, we show supremum of AS is equal to A times supremum of S. But here infimum of AS is equal to A times infimum of S. We can verify this property by a simple example. For example, suppose our set S is consists on first 20 natural numbers. If I ask what is the infimum of set S, the infimum of set S is 1 here. The infimum is the greatest lower bound. Greatest lower bound is an element which is less than or equal to every element of set S. So infimum of set S is here 1. We let A, the fixed real number A is 3. Now we define a new set 3S, which is actually the product of these elements with 3. So we have 3 to the 6, 9. The last number is 90. Okay. Now what is the infimum of this set 3S? The infimum of this set 3S is equal to 3. Whereas on the other hand, if we calculate 3 times infimum of S, 3 times infimum of S. What is infimum of S? Infimum of S is 1. So this is also equal to 3. So this property can be verified by this simple example. So now we prove this property in general. Since it is given that S is non-empty subset of real number R, and further it is given S is bounded below. So because this is bounded below, so by definition of bounded below set, it has a lower bound in R. So S has a lower bound in R. Further, since R is a complete ordered field, so by definition of complete ordered field, infimum of S must exist in R. So let U is infimum of set S. So this is this as an expression number 1. Now we shall show that infimum of AS is equal to AU. This is our final target that we have to show. Infimum of AS is equal to AU. What does this expression shows? Infimum of AS is equal to AU. This expression shows that AU is the greatest lower bound of set AS. So this is our final target that we show, that we need to show AU is the greatest lower bound of AS. AU is the greatest lower bound. To show this, we will find a lower bound other than AU, and then we will show that lower bound is smaller than AU. This will show that AU is the greatest lower bound. So start from expression number 1. Expression number 1 says U is infimum of S. If U is infimum of S, then by definition of infimum of the set, U is smaller than or equal to every element of set S. So U is less than or equal to S. To make this expression AU, we multiply this expression number 1 with A on both sides, we have AU less than or equal to AS. Say this is an expression 2. Now, what does this expression 2 shows? We can notice that AS is an arbitrary element of set AS. AS belong to the set AS. This is set. AS is an arbitrary element. This is an arbitrary element of set AS. If AS is an arbitrary element of set AS, and this arbitrary element is greater than AU, this shows that AU is lower bound of this set. AU is lower bound for this set. Since AS is an element of AS, so 2 shows that AU is a lower bound of set AS. Next we shall show that AU is the greatest lower bound of AS. That is our final target. AU is the greatest lower bound of set AS. This is our final target. To show that AU is the greatest lower bound, for this we show there is a real number V which is an other bound of set AS. And finally we show that this V is smaller than or equal to AU. Let V belong to R is an other lower bound of the set AS. Then because we have supposed V is an other lower bound of set AS. V is another lower bound of set AS. So if it is a lower bound, then every element of set AS will greater than or equal to V, where S belong to capital set S. Now we convert this expression for the elements of set S. For this we multiply on both sides of this inequality with 1 by A, or simply divide both sides by A. So when we divide this inequality by A, we have S is greater than or equal to 1 over AV. As S is an element of set S, this shows that every S, because S is an arbitrary element of capital set S, so S is greater than or equal to 1 over AV, shows that 1 over AV is lower bound of for the set S. So 3 shows that Three shows that 1 over AV is a lower bound of set S, so U is equal to infimum of. Now, if 1 over AV is a lower bound of set S, 1 over AV is a lower bound of S. This implies lower bound of S is always less than or equal to greatest lower bound of S. Lower bound of S is always less than or equal to greatest lower bound of S. What is lower bound of S? 1 over AV is a lower bound of S. What is the greatest lower bound of S? The greatest lower bound of S is the infimum of S, that is here U. This implies U is greater than or equal to 1 over AV, or simply 1 over AV is less than or equal to U. Multiply on both sides by A, we have AU is a greater than or equal to V. As we have supposed that V is a real number, that is a lower bound of set AS. Now we show AU is a greater than or equal to V. This shows that AU is the greatest lower bound of set S. This implies AU is the infimum of set AS, or simply by replacing U is equal to infimum of set S, we have our required. So I hope today's lecture is helpful for you, and thanks for your watching. If you have any doubt, any query or question, you can comments me, inshallah I will reply you. See you in the next lecture. Take care. Allah Hafiz.